Welcome back to another episode of Dominic Does DIY. I hope you have been enjoying the videos thus far, and if you have, please like, subscribe, share the video, and now let's get on to it. Today you were so proud. You found a pretty decent current gain amplifier circuit online and ran it through the simulator using an ideal op-amp. You figure you can just simply make sure you have a rail-to-rail input and output op-amp, and that should be close enough to take this live so you don't have to bother with finding the P-Splice model and converting it for the op-amp you want to use. So what does the gain amplifier do? Well, the current gain amplifier will take an input, a current input, and amplify the current into the output of an op-amp. So the I out of the op-amp is equal to your input current times the gain of the circuit. So let's run the circuit real quick. So you can see here our input, the IR8 is 1 milliamp, and the current through the op-amp output, which is this IR6, it is 6 milliamps. So this is perfect and what you wanted. You wanted a current gain of 6, and that is what you've got. However, when you put this in action, it just didn't work at all. Things were just not making sense in the real world compared to the simulation. So you decided you need to go back and do some more research into how this circuit actually works, so you can modify the circuit in the real world in order to get the output that you desire. So what you need to do is the following. Analyze the circuit to see what is the gain of the formula. 2, determine what reason behind it failing was. 3, correct the circuit in a way to allow it to function as expected using a rail-to-rail input and output op-amp. And 4, list the limitations of the gainability of the circuit. Pause the video now if you would like to take some time to analyze this yourself. Otherwise, I will give my solution shortly. Okay, so for part 1, we need to analyze the circuit. We know no current can enter the op-amp at the input nodes, N plus and N minus. So all current has to go through the feedback resistor, RFB. We also know that N plus equals N minus, which is equal to 0. So voltage at RG, which is labeled as VA in this diagram, equals N plus minus input current times the feedback resistor. Already we can see an issue. We have a single supply system and we are starting to register negative voltages. So what is the current through RG then? Well, IRG equals VRG over RG. Since VRG is negative, the current is negative, which means current is going from ground to this node and then into the output of the op-amp. So current going into the op-amp is going to be the current through the feedback resistor and the current through the ground resistor. So we know that the current through the feedback resistor is just our input current, and our current going through the ground resistor is equal to our input current times the feedback resistor divided by the ground resistor. Or if we simplify this, we can see that it is the input current times 1 plus the feedback resistor divided by the ground resistor. So the gain of this circuit is actually 1 plus our feedback divided by our ground. The voltage at the output of our op-amp is just going to be VA minus our output current times our output resistor. When we do this, our voltage at the output of the op-amp is going to be heavily negative. So when we went into the real world, things went all squirrely as the op-amp tries to compensate with its working voltages and whatnot. So here we can see it looks good using an ideal op-amp, but when we get into the real world, the simulation doesn't really show us what's going to happen in the real world, and that's why we have to go through these calculations. So now part 2, we have to determine what the reason was behind it failing. Well, the reason were these negative voltage levels. So because of that, the op-amp couldn't compensate correctly, and so the formulas weren't working. And then part 3, it was correct the circuit in a way to allow it to function as expected. So how can we make this circuit work? First thing, we might just think to bias the op-amp to try and elevate the system. If we just try and bias with, say, 2.5 volts, the system does not gain like we expect. It is because the op-amp will no longer sink current but source it. So we lose the gain feature of this circuit because instead of our output current being equal to the feedback current plus the ground resistor current, Instead, we have our ground resistor current equaling the feedback current plus the current that our op amp is going to supply. So this won't work for us in this system. What we need to do instead is create a floating ground. So using another op amp, we can create a buffered floating ground voltage source for us. This will allow us to reach a lower voltage at the VA node than the ground reference. So here I'm just using an op amp, a voltage follower circuit, just to give us a buffered floating ground. And you can see I'm just making it half VCC. So in the world of this op amp, because where we're using this floating ground with the in plus pin, and then we're using the floating ground for the ground connection for the ground resistor, then in the world of this op amp, it's actually going to be in this circuit, it's going to be in its own little world where it's going to see basically plus 2.5 volts and minus 2.5 volts. So now our VA and everything can drop down without actually dropping below ground levels. So in the world of this op amp, it's not actually going to see a negative voltage, but in the terms of how the op amp calculates its gain function, it will see that negative voltage. So we'll be able to do what we want to do, which is get that current gain amplification going. So part 4, what are the limitations? What is the maximum we can do, and how can we manipulate this so that we can achieve a little bit more? So our circuit started out basically with these values in there, with our feedback resistor 1.5K, our ground resistor at 300, and our output resistor as 10 ohms. So what we're going to do first is real quick so we can see how this floating ground affects it, because we were running ideal op amps before. So what I want to do is I'm going to go ahead and run this circuit one time, and I'm just going to put the grounds back in how it was originally, and we're going to try to just use this because now we're no longer using the ideal op amp. Now instead of the ideal op amp, we're using this LT1807. So if we run that, you can see that our current through R2, the current through our feedback resistor here, it is 1 milliamp, just like we expected to, since that's the input current. But I3, which is our output current, we can see that it's actually a positive 0.9 milliamps, right? And so what that means is instead of getting, we're getting less current at this point than we were expecting. Remember, we were expecting a gain of 6 if this thing was operating correctly, because it should have been 1 plus R feedback over RG. So with our R feedback at 1.5K and our RG at 300, then that means that we should have like a gain of 1 plus 5, and that would be 6. So if we have 1 milliamp in, we should see 6 milliamps out. But we actually are pulling less current than expected. It's because the whole system is messed up right now because of that voltage aspect. So if we look at our voltage here, it can't go to the negative region that we need it to in order to do the gain application. So what are we going to do? Well, we'll just go ahead and swap out these grounds, and we'll put back our floating ground that we were using. And then rerun it. And now you can see, just as expected, we've now got the 1 milliamp input current, and we're getting our 6 milliamps out of our output resistor, out of the output current. And that's because now we're dealing with this floating ground, so things can now go negative like they're supposed to. And remember, the major limiting factor on this is the fact we can't drop below 0 at the output of our op amp, right? Because our whole system, that's the system ground, so we can't go any lower than that. We don't have negative voltages. So that is our limiting factor. As soon as the op amp output voltage reaches 0 in the circuit, it starts to be unable to gain anymore. So now the question is what is the limitation of this circuit? So right now we're running transient 5 seconds, but instead of a transient 5 second, what we'll go ahead and do is we're going to go ahead and change our simulation profile from a transient, and we'll go ahead and just so you see what I'm doing, it's I'm I'm just typing this stuff in to change them over here because I got my DC and my transient here. So if I click on that, it pops it up. So you can see we got our start value is going to be 1 milliamp. Our stop value is going to be 10 milliamps. And we're going to go ahead and increment within at 10, microamp increments up to that range. And so now when we sweep this, you can see our input current is going up like we expect. But let's actually look at something else here. We want to see our output current, and then we want to see that in comparison with our output voltage. So we can see here in this first section over here, up until about 1.5 milliamps, about 1.56 milliamps, we have a nice linear translation, right? So this is the good working region of our op amp and our gain function. So with these applications right here, we can see that we can go all the way up to an input of about 1.5 milliamps and be able to accurately get our six-figure gain. But as soon as you reach over 1.56 milliamps, the voltage on the output of our op amp, it drops to its low point. It can't go any lower. And as soon as that happens, that's when we start losing control of our gain function. So this thing will work, this circuit right now as is, will work up until this part right here, till about 1.55 milliamps. I also created a spreadsheet, so just to be able to calculate this stuff out. It's just all those formulas that were earlier in the video. So if you want to go back and look at that, you can basically make this same spreadsheet. And so we can see here that the output of our op amp is calculated right there. So if I go ahead and put 1.55 milliamps there, you can see I'm starting to get close to 0 on the output of my op amp, and that's where it's going to start to fail, right? So as soon as I start going below that, let's say if I crank this up to 2 milliamps, my output voltage now goes negative, so I'm done. I can't go any farther from that, right? So that's about the limitation on this one is about the 1.55 milliamps as an input to be able to keep the gain of 6. So now the question is how can I, or what can I do in order to be able to get to a higher current, right? Like, let's see, how far can I extend this 1.55, or what can I tweak in order to kind of manipulate this to say, let's say I wanted to go up to 4 milliamps as an input current and be able to output 24 milliamps from this op amp and this gain amplifier. Then right now, if I just try to crank 4 milliamps, obviously I'm going negative 3 volts, so this isn't going to work. Then what can I do to manipulate it? Well, remember how the formulas are written. You got your V out is based on your VA minus the voltage drop across your output resistor. So how can we reduce that voltage drop on the output resistor? Just make it smaller. So one of the easiest things that we can do right off the bat is instead of using a 10 ohm resistor right here, we just take this down to a 10 milliohm resistor. I don't know why I chose to do this in kiloohms, but I'm not going to redo my formulas right now. So that's 10 milliohms that we have right there. And now you can see that as soon as I did that, it helped out a little bit, but not a whole lot, right? Like if I go back to the 10 ohms, you can see I got a 0.08. And if I take this down to 10 milliohms, I go up to 0.17. So what does that do for me? Can I get up to 2 milliamps? No, right? So 1.65. So it doesn't really do too much for me, right? Like it gets me to maybe 1.62 or something, 1.62 milliamps, but it doesn't do a whole lot. In fact, when we show this, I remember the old one. If I put my cursor down here, you can't read it, but it's like 1.56 milliamps. And if I run this now with the 10 milliohm right there, yeah, you can't really see the difference here, but if I stick my cursor down here, I can see it's about 1.62 milliamps. Basically what the thing calculated out. It helped out a little bit, but not a whole lot. So what else can we do? Well, the other way to increase the ability of this system is to, if we can't really adjust V out that much, well, we can adjust VA. How do we adjust VA? The VA formula, right, to get VA, it was just our input current times our feedback resistor. So if we can drop our feedback resistor, then what will happen is our VA will begin to rise. And when our VA rises, then that means that we're allowed more of a voltage drop across R3. And because our feedback resistor is so much larger, if we adjust that, we can actually make a pretty big dent into our range of what we can do. Remember, it is the gain of this resistor is 1 plus our feedback over RG, so we still want to stick with our 6 gain. Our AV equals to 6, so that means that we need our feedback over RG to equal 5. So if we just keep with these sentiments, right, we will just say instead of 1503, we can divide each of those by 3, and we end up with a 500 ohm resistor and a 100 ohm resistor. And we'll just keep the 10 milliohm resistor there for give us that little extra boost. But you can see now my output voltage, it went all the way up to 1.69 down here. So what does that mean? Now, remember that I was saying 4 milliamps as an input. So can I get to 4? I can get to 4 milliamps quite easily. I can actually go beyond 4 milliamps just by adjusting that one resistor right there. So let's go ahead and change those inside our simulation. And we're going to have a 500 ohm resistor there and a 100 ohm resistor there. And now we run it. And you can see our line gets extended all the way out to 4.517 milliamps before the output of the op amp becomes saturated on the low end. So now we can get out to beyond 4 milliamps as an input, which means we can get to 24 milliamps on the output, which is really good. The only other thing that we'd have to calculate is the current, and are these op amps able to handle it? This is very small, like even with a 4.5, like you're looking maybe 30 milliamps as an output, right? We can see up here, so when it saturates, the op amp is going to be sinking 26 milliamps. That's usually nothing for an op amp. That should have no problem being able to sync that. And now we've got our gain against that R3 resistor just the way we want it. So there we have it. That's the video. I hope you learned something from this, or you took some, got some information out of it. And that's how we're able to make a current amplifier. Most people use op amps for voltage amplification, not really current amplification. And you would have to find a way to incorporate this current amplifier into your circuit. There's other current amplifiers out there. Like you can use 2 BJTs and whatnot. So there are some other options out there to do it. I just chose this one because I thought this was more interesting as an example. But you would have to figure out a way to kind of put that R3 into your circuit. So it does make this one a little more complicated as a gain amplifier to be just using as opposed to a BJT system. But I hope you enjoyed this episode. And if so, please like, share, subscribe, and keep doing stuff and getting better. Until next time.